Great. Okay. Um, Unfortunately, there wasn't a ton accomplished for me, but let me talk about sort of what I was trying to do and where we are and what I think needs to happen going forward to what I was hoping to accomplish to work. Of course, the big picture of ZKML is that it's a way to kind of let a blockchain perceive soft information from the physical world, identity information, and to let smart contracts exercise judgment and to create kind of on-chain, unstoppable AI, run machine learning models as though they were on-chain. And the product that we have that sort of predates this is this thing called Ezekiel, which lets you take a baked model from PyTorch and turn it into a zero-knowledge proof. And this thing is an open source project. It's based on Halo 2, and you can define basically some kind of tensor manipulation, arbitrary models as neural networks, and then it transforms it into a proof. But so it uses a couple of things in a crucial way. It does some clever quantization, and it does some uses nonlinearities, implements nonlinearities as lookup tables. And you can describe the thing, you can create a proof, serialize the proof, and verify the proof. And I wanted to take that and be able to verify the proof on Mina. That was sort of my goal with this effort. And the big picture for me is from the point of view of a user. They start with a model in PyTorch or Onyx, then they create a compiler, use a compiler to transform that into different proof systems, either fuse or lowering the operations. And we're looking at Halo 2. And in my mind, Mina is very closely related in terms of proof systems. Kimchi system is very closely related to Halo 2. A lot of the same choices, a lot of the same ingredients. And so my hope was that it would be fairly straightforward to translate, but unfortunately that's not what I found. And then the way that we want to scale these models is basically a combination of hand tuning, optimization, aggregation, proof aggregation, recursion, which I'm hoping is something that, because Mina has it natively, we can use that directly, and then this kind of fusion of operations and composition, which is also, I think, relevant to incorporating Mina either way. So just again, the objective is just to try to allow these models that we can produce to be verified on Mina and to make use of native recursion so that you can do, for example, evaluate something, a layer, and then go on to the next layer, and so on, without having to fit the whole thing into one proof. And that's really powerful for obvious reasons. It also lets you improve the privacy situation, because the later layers don't need to know as much about their other layers, depending on how you set that. I want to say a word about the way the quantization works. So, of course, your underlying model is of floats, 32-bit floats or 16-bit floats, and you quantize those to field elements. We do that with machine learning models, neural network models, but usually that quantization is purely for performance on limited hardware, and there are somewhat different choices made from the kind of quantization we have to do for zero knowledge, where it's really obligate. All we have to work with are the field elements. And so you can do that kind of quantization work manually for single models, and you can do a lot of shortcuts. But then what we can do is work with sort of general models, automated strategy. And there's some numerical issues where you have to correct for tolerance and numerical problems because of the quantization. And there's a lot of neat work to do there. The situation right now with Mina is that, as I said, we currently depend on lookup arguments, both for the nonlinearities defined in the neural network and for aspects of doing the quantization itself. And while Kimchi supports limited lookup, the situation right now, as I understand it, that the functionality is not exposed to zkApp developers for lookup to be able to use lookup tables. And I think it's not on the roadmap as well, as my understanding. And so that means that all we can do are models that we can express, with Planck or optimization with some kind of polynomial systems of polynomials. And right now, that's a limited set of models. And so I see there as being kind of a couple of different possible ways forward. I'm writing a blog post to summarize, for you guys to summarize this kind of what I found. I think the good options are, if it's going to be into SnarkyJS, if it gets into the roadmap, then user-defined lookups. That's something that we would use immediately. I think another good option, but one that's quite a lot of work, that maybe you guys want to do, or some other team wants to do, or I don't know, maybe I'll be involved, is to write a Halo 2 verifier in SnarkyJS. Right, so to write a verifier for another proof system that does support lookups. And that, there's precedent for that. There's an EVM verifier, for example, that is a separate system, and that was also pretty hard to do. But so it's not crazy to do that, and that might be the most sort of all-purpose way to deal with it. And then you can just kind of use off-the-shelf Halo 2 inputs. So that's sort of interesting, and because it's already using pasta curves, that might actually work well. I don't know. I'd say the less appealing options are to kind of lower to just a polynomial representation, but that really limits the size and the interestingness of the models you can do. And then another kind of crazy option is to use a bridge. So verify it somewhere else, and then bridge the result into Mina using like an Oracle strategy. I find those two kind of unsatisfying because I really want us to be able to verify natively. So yeah, that's it. So I hope I'm not ending the project in the sense that I still want to accomplish that first goal of getting it to run. I just realized that it's sort of beyond the scope of what I could do during this program. So I have to continue to stay involved and either wait for it to happen or make it happen, depending on how the world evolves.